How's it going, everyone? Elier Gonzalez here. So let's go to explore now the functional light JavaScript version 3, which is a course taught by Kyle Simpson based on his experience of how can we use now this mathematical tool set when it comes to write applications that are less error prone and provable, which is making our code much more easy to debug, to maintain, and to fix. Now, you might wonder is why this is important, why this is relevant, because at the end of the day, this, or as a JavaScript developer, you are going to write a lot of code if you're building something, but also you're going to read a lot of code if you're going to provide your services to any company, right? And because of that, and since the vast majority of the time all of those code we're reading is by people, not you, perhaps sometimes code that you ship, but it was using now a particular paradigm when it comes to write JavaScript applications for other authors, and that is known as the imperative approach. You tell the machine, you tell to the JavaScript, hey, this is how I want you to do this stuff that I want you. There is nothing wrong with that. In fact, this is now an imperative approach. This is the way of how we most of the time have write this kind of application. But the problem with that is that anytime you work for a particular company, or you're trying to now find a way to add, fix, or debug a company's website, whether it is on SaaS or any other open source tool that they might have, especially reading on JavaScript, exclusively in JavaScript, it becomes very, very hard to read and understand and to make sense whoever wrote this, whoever was the author of this particular code. So now you can actually fix or add a new feature or do a refactor of this code. So that's the value proposition of the functional programming. So instead of actually us having to tell the machine what exactly needs to be done, we are going to be more explicit about it. In other words, we want to know is the output of this and what the things does, at least more in a more technical aspect. So this is also the reason why we're actually exploring this, and we want to get a more hands practical approach, at least with the company that I'm working, which is Banco de Chile. And yeah, so let's get into this. Okay, and yeah, this is part of the structure of this particular code. When it comes to now have all of these different tool sets under our tool belt, to now anytime, especially in JavaScript applications, we need how can we actually provide this or how can we apply this tool. Why this is important, especially if you're going to write any JavaScript application, whether it's on the front end or on the back end, you want at some point have now a consistent way of make your code, as I mentioned before, less error prone, improvable, aka make your code, which is also that he mentioned here, at least Kyle Simpson, as a way to get a little bit of history here, is that wouldn't it be nice if we have now a code that 80% of that were mathematical proof, and that stuff is going to work as long as you use it, and you can only focus on the business logic. And again, this is the value proposition of this. So because Kyle Simpson, shout out to Kyle Simpson, man, that he dedicate time to actually boil down all of these particular tools that pretty much like when you go out on a restaurant and you order a dinner and you take the bill. You don't need the mathematical proof of why the addition, subtraction, multiplication, and division works. You just use that tool to actually pay the bill and split that to your fellow friends. Or if you're inviting a woman, all right, you pay the full price, all right. But the whole point of this is recognize that in our daily life we don't need to go with this mathematical proof of why 1 plus 1 is equal 2, all right, or why when we multiply a negative number is it gives you now the opposite sign. So for example, minus 1 times minus 1, it gives you now a positive. Okay, you don't need to mathematical proof. And again, a lot of functional developers and engineering where they actually find joy into getting to this mathematical description, mathematical proof about why things are they are. I'm not done. I'm definitely not done here. I am not there. I am not there. Absolutely. So because of that, we're going to rely on these particular tools. Why we're using these tools? When can we use these tools as a way to now apply that into our code? So we need to now provide this provide these services to any companies. We can be very, very effective and efficient of doing so. Now, there is a functional programming journey that he mentioned and he described, which is you might initially started to understand that, right? So you start with the imperative, all right? So imperative at the beginning might be quite readable until you reach a point of the pit of despair, especially when you read someone else's code in an imperative way. When the author of that code say, hey, this is the thing that I want you to do, and this is how I want you to do that. So it becomes quite hard to know and to figuring out how these things work. A good example of this is when you're starting to develop algorithm or this sequential way of doing stuff, like bubble sort or binary search. If you don't know how the things work, then you need to look at each one of those stuff and how that things work. So if you can imagine this, which is a solution for solving a lot of problems, searching and sorting, which is the reason why the computer science and programmers actually are paying for. I want you to, you can think of this like a librarian, okay? Hey, I want you to do your own magics, okay? And the way you do that is by, here's the data, the company data, whatever it is, with depend of the industry, it can be also quite sensitive, okay? Here's the data, and I want you to organize, apply your spell on this data sets, so we can now is sort things quickly, query elements, and sort it and searching, right? These two important things. That's why, and I get it why a lot of people focus a lot in data structures and algorithms, because the idea is that you're going to get yourself familiar of what are the tools, the essential tools that we're going to use in our daily life, as well as techniques that we need to know as a way to make our life much more simple when it comes to look patterns, right? So I think this is a relevant and revealing part of the journey of programming, of computer scientists, or a software engineer, right? So because this is how you can actually what this is describing is the journey of a functional programmer. That you initially start with imperative, and then you realize that it's quite hard to read, to understand, and therefore even to fix. All right. Now, with the functional programming or the declarative programming, initially it can be parsed. This Harry Potter language that they developed to talk with snakes, you know, it can be Mandarin, it can be Chinese. It is fuzzy. It's not from this world, you know. So, how can we solve this? At least initially, is by continuous pushing up and understand that at some point you might not end up absorbing all of this concept in one go, but the more you keep pushing and the more you are going familiar with how the things started to work, the better off will be for yourself and for whoever is going to receive your services, right? So that's the value proposition of functional programming, based on the Kyle Simpson words and also my experience. Is that the TLDR is that by looking at this mathematical tool sets that we now are in the mathematical bedrock. So by using this, we don't need to guarantee or verify that these things are going to work, because it will, and therefore now we can focus on the business logic. That's the entire value proposition of this. So let's going to use this mathematical proof to make our code much more readable, and therefore easy to maintain, to debug, and to fix. Period. So yeah, the code is provable and less code to read, because if we follow now these mathematical principles, you can focus your attention to what is really important, which is the business logic. And yeah, that again, I just want to bring that up here quickly, at least in this 10 minutes. All right, and well, let's get into what is the tool set that we can use here. So course overview, functions, closures, composition, immutability, recursions, lists, and data structure. This is what we really know about the map and filtering, all that kind of stuff. And then the asynchronous nature. So how can we use, this is interesting because stuff like promise and observables are now based on this mathematical foundations of how can we deal with asynchronicity in our language. That's mind-bending. That's mind-bending stuff. And then functional programming libraries. Cool, good. Now, first we went through functions, because at the end of the day, since this is functional programming, we need to have a very solid definition about what a function is, right? And functions versus procedure. Most of the time we are quite familiar with procedures, which is this set of instructions that we now encapsulate into a function. But most of the time they don't return something. They don't do anything. They just do internal stuff, but they don't return something. So this is procedure, and most of the time we have is procedures. But now, if we, for example, have true function, which is takes the inputs and returns something based on the inputs. So a great way to describe now a function is, what is this? What is the relationship between is the inputs and the outputs? And that's the next step of how you can describe is what this, what is the name, what is the semantics of this function based on the relationship between its inputs and the computed output, right? So this is when we look at here at this particular function, which is whoever input that you pass through, it will be reflected as the output. So in other words, this function that we describe here, based on its input, what is the relationship that it has with this computed output, right? In this case, we can call this this is now the quadratic graph. All right, so pretty good. Yeah, this is the quadratic. No, I mean this is the wait what? No, the quadratic graph. What? Yep. Exactly. I'm not quite familiar with the terminology on English because I mainly receive my instruction on Spanish, so I'm more aware of this on Spanish, not on English. But in any case, yeah, the quadratic function. So you can say by mapping the inputs and it is computed output, and this is the key word here. That's the key word here. The goal here is to create relationships or mapping the inputs with the computed output, and based on that, all right, then you now provide a semantic. So then you now describe this. That's slowly but progressively starting to make a lot of sense, especially if you're creating functions. So the idea is that how you're going to map is the inputs with the computed outputs. Function name semantics. And function, the semantic relationship between the input and the computed output. So in other words, what is the mapping between the input and the computed outputs? And based on this mapping, when you pass a lot of input to this, and then you get a lot of outputs, then what is the semantic of this? So this is a good example of this. This is interesting because here we enter into the realm of data analysis. Here we enter into the realm of data analysis. Analysis. Interesting. Data analysis. Given this huge set of data that now are going to apply some sort of transformations to get an output. So we want to know is by applying this transformation in these functions, what is the relationship here? That's quite interesting. That's quite interesting. That's quite interesting. Okay, good. What is a data analysis? It's the science of analyzing raw data, exactly. And then they transform that kind of stuff, and so on and so forth, blah, blah, blah. Data analytics techniques, regression analytics, factor, cohort to Monte Carlo. I love the Monte Carlo simulations. And this is data analytic techniques, regression analysis, factor analysis, cohort, Monte Carlo simulations, time series analysis, data analytic tools, for example, Excel. All hail to Excel, bro. All hail to Excel. Statistical analysis, data representations, so forth, so on and so forth. But again, I mentioned this is because now we have is a practical, which is this is something that, for example, when you go into your math classes, perhaps in 8th grade, 7, 8, 9th grade, right? And you'll see all of this drawing and abstract stuff that you don't see any real life application, and they have a lot, and they can provide you a lot. And they can provide you a lot. So for example, basic arithmetic, they can provide you a lot, bro, a lot. But most of the time, we look at all of this stuff as something that is far away. It's like distant. It's We don't know. We don't care. It's like this is this is stuff that we don't see any real life applications. The arithmetic, yes, of course, or the basic arithmetic, but with the algebra or drawing, well, this is part of the algebra, the quadratic function, but with the algebra in mathematics, quadratic function is a variable in a function. Is this what is this exactly? This is some schematic description here, but with this formal definition, no, partial functions. Well, this is part of the functions, and functions can be entered into the realm of algebra, I think it is. Functions, graph univariants. Yeah, wait. List of mathematical functions, algebraic functions. Here we go. You know, algebraic functions. Even though that I haven't received any formal allocation for this, but I make the link, I make the relationship. Why? Because algebra means broken part. How you can make all of these broken parts, and for our use case, how can we bring all of these missing pieces, all of this broken part into something that provide meaning? And elementary transcendental functions. But again, this is part of the algebra, right? An algebraic function is just a fancy way to say from the algebra is this missing pieces. How can we now broken parts of this, or how we algebra is the decomposition. Or algebra stands for what's algebra stand for? Algebra, etymology. That's right. Javara. Interesting. Reunite, restore, the reunion of broken parts. So we have all of this different stuff here, split them, and how you can now combine them together. Algebra. Oh my God, medieval. This is why this is one of the reasons why again it go a little bit beyond the scope of this, or is part of the course here. But this is why we look at this: the evolution of software architecture and the woven of loom of sorrow, especially a history of computing, bro. A history of computing, thanks to Grady Butch. Let's go back here. So algebra here, it means that it's the reunion of all of these broken parts. So how now in this code, in this function, the relationship of this function, okay, is that, hey, how by putting one input and get a different output, and another input and a different output, and another input and a different output, and all of these different broken parts, how can we reunite them, and to use that, how can we create the relationships? What is the relationship between the inputs and the outputs? And that's exactly what we're going to do here. So the TLDR of this, by exploring now the function purity, the difference between functions and procedures, and then function name semantics, and that kind of stuff, is to understand that functions is the semantic relationship between the input and it is computed value in the sense of JavaScript. But that's not enough, because we need to look at other properties that makes now the code provable in the functional programming, and that is that the code must not have any side effects. In other words, it must not change the state outside of this. It must have a close relationship, okay, like this. It must have a close relationship with the inputs and the computer outputs. So avoid side effects with function call if possible, right? And some common side effect is that, hey, perhaps this function needs to communicate with external devices, all right? Peripheral, input and outputs. And that include is, so database and storage, network calls, or even the DOM. This is now relevant to JavaScript, okay? Even the DOM or timestamp, random numbers also generate is side effects. Anything that you can map between the input and the computer output, it is a side effect. So the computer sense is, well, the input and output, so communicating with the so for example, console log files, so communicating with a database or with another computer, with the DOM, so timestamp, because it will be or random numbers, and even though it's going to create now CPU hits and CPU time delay. So let's get into this of that. So it makes a ton of sense. It makes a ton of sense. It makes a ton of sense. But a ton of sense. Okay, let's get into this.
So these pure functions that we're talking about, what does that mean? What do we mean by a pure function? Well, the first way we could define a pure function is, as we have defined so far, it is a function in the spirit of functional programming. It is a function that takes all of its inputs as direct, all of its outputs as direct, and it has no side effects. That's the first way of thinking about a pure function. But remember, and we'll come back to this in a bit, remember that I've pointed out, it's not about the function definition itself for JavaScript, but rather about the function call. There really isn't such a thing as a pure and it has no side effects. That's the first way of thinking about a pure function. But remember, and we'll come back to this in a bit, remember that I've pointed out, it's not about the function definition itself for JavaScript, but rather about the function call. There really isn't such a thing as a pure function per se, as there is a pure function call. That's the thing that we want to go after.
Okay. In computer science terms, specifically JavaScript, a pure function is not in the sense of functions definition, but in the function call, and that makes a lot of sense. Okay, but in the function call, so a pure function is a function without side effects. Okay, that is just now have the relationship closely related, right? Is now have is a function that doesn't change anything outside of that function. It doesn't mutate any state outside of this function.
So yes, we could look at the add to function, and if we were to call it with two inputs and get a single input output out, that would be a pure function call. Add another here, however, line 7. It takes two inputs, yes, but notice how it also uses a z variable that's outside of it. So that's an indirect input. And in the strictest sense, using an indirect input invalidates something about the nature of what we were supposed to be able to expect about this function. We're supposed to be able to prove and predict its behavior, and because we're relying upon a side cause, a side effect, now we can't really be as sure, we can't really prove it through the math. So that's the kind of thing that we want to be aware of. is if we're accessing variables outside of ourselves, is that invalidating? Is it removing? Is it watering down those benefits from functional programming?
Water it down. Water it down.
Variables outside of ourselves.
What?
Is that invalidating? Is it removing? Is it watering down those benefits from functional programming?
Watering down. Okay. Watering down. What the French is those? Watering down. Watering down. Oh shit. I wouldn't diluir. Oh crap. Oh my god. That's one of the reasons I also take this stuff, because holy moly, bro. Watered it down. There, you got it. Okay.
We want to be aware of is if we're accessing variables outside of ourselves, is that invalidating? Is it removing? Is it watering down those benefits from functional?
So if we this is now specifically to JavaScript, if we are now accessing variables outside, exactly, if we're now accessing inputs outside of the function, we are watering down. I love it. We are watering down is the benefit of, and I love it, bro. We are watering down is the benefit of functional programming, bro. If we're now accessing inputs, if we're now accessing outside inputs in our function, or in the function, we are watering down the benefits of functional programming. Holy bro. Watering down.
It's more complicated. It's not just that we can't access a variable outside. We talked about all the other kinds of side effects, like generating random numbers and all of that stuff. But it's also the case that we could access a variable outside of ourselves and not invalidate our function. It is more complicated. But that's a clear signal. It's like a usual suspect. It keys you in. If you see an access of a variable outside, immediately you should be asking yourself, why? Why is that? Is that necessary? Is that useful? Is that important? Because the code might look like this. The code might have a z variable in the outer scope. And in this case, line 1, it's a constant, z equals 1. Now, if on line 8, instead of accessing z, if I had accessed just the value 1, if I said add 2xy, and then just said plus 1, we would all say, no problem. That looks like a pure function, no side effects, no side cause. So is the introduction of z here really a side causer? Because if we think about what a constant is supposed to be, a constant is supposed to be a semantic placeholder for a value. And especially since we're using the const keyword, but even if we weren't, because it is a constant, it doesn't change throughout the lifetime of the program. So really, is it invalidating this as an impure function, or is add another simply referring to a semantic constant placeholder? If you could convince yourself that line 11 is a pure function call, and there will be more layers of meaning to what we mean by pure function call, but here, add another does in fact return to us the value 42 when we pass in 20 and 21, and it doesn't change anything else about the state of the program. So it doesn't cause any side effects, and it doesn't use any side effects other than this constant. And I would submit to you that it is therefore still consistent with functionalism. That line 11 still counts as a pure function, even though we're accessing a variable outside of us. Now, you may be able to convince yourself that that is true because I pointed out that we're using the const keyword. But when I switch it up and I say, oh, whoa, what if I use the var keyword? Some of you may be saying, well, now it's not a pure function. Really? Is my choice of const versus var here actually going to impact the readability of this program? Some say yes, but I'm going to say, I don't think so. And here's the reason, and this is critical for all the rest of our discussion. If it were possible for me to show you a code snippet that only had part of the program, and I were to ask you questions about it, and I was only showing you part of the program, then you could say virtually anything. Because just about anything else could also be true in that other part that I was hiding, right? So it's, in a sense, not useful to discuss a program unless we're discussing it in its entirety. For the purposes of our discussion in this course, we need to assume that we see the entire program. So let me ask you the question. Anywhere in this program, does C ever get reassigned?
No.
We see all the lines of code, and we know that it doesn't get reassigned. So let me ask you a question. Is C serving the purpose of a constant in this program?
Yes.
I would submit that it is. Whether it used the constant keyword or not, it is a constant in practice. And therefore, every bit as much in the spirit of functional programming. Now, I know many functional programmers that are absolutely enamored with the constant keyword. They use it all over. I don't think the constant keyword buys anything for the function. Because the real important key is the variable getting reassigned, not can it be reassigned? And in fact, more important even than whether it gets reassigned or can it be reassigned, is it obvious to the reader that it can't be reassigned, that it doesn't get reassigned? Is that obvious?
Const no.
Because it looks like it's making values that don't change, when actually it's making variables.
Variables that they don't get reassigned. Exactly.
Topic when we talk about. But I would submit to you that in this program, C still serves that role, and therefore add another is still, when it's called on line 11, that's still a pure function.
Because we're talking about here the function calls, bro. It's because we're talking about the function calls, bro. The following code. Okay. Okay, so what we're doing is now putting these sunglasses here, these special sunglasses, to see how now can we look at stuff. Okay, the following code is indeed a pure function. Why? Because despite that the snippet in the add another function is okay. Why? Because despite that the snippet in the another function is calling a variable outside of the it's calling a variable outside of the function definition, when we call add another, so when we call add another, which is screen, let's find it. Why not? Okay, I'll find another. This one. So when we call another in line 11, okay, so when we call another in line 11, we are going to see, okay, so when we call add another in line 11, we're going to see exactly. So we are not redefining the const or var C. So the following snippet follows a function purity in terms of function call rather than function rather than just function definition. Okay. Holy fuck.
If you could convince yourself that line 11 is a pure function call, there will be more layers of meaning to what we mean by pure function call. But here, add another does in fact return to us the value 42. Boom.
Exactly. But this is again in terms of add another function call. And by the time that you do this, you will always get that. So the relationship here between the input and the computer output remains the same, remains consistent.
We pass in 20 and 21, and it doesn't change anything else about the state of the program. So it doesn't cause any side effects, and it doesn't use any side effects other than this constant. And I would submit to you that it is therefore still consistent with functionalism. That line 11 still counts as a pure function call, even though we're accessing a variable outside of ourselves. Now, you may be able to convince yourself that that is true because I pointed out that we're using the const keyword. But when I switch it, this might only full to at least we can see all the lines of code, and we know that it doesn't get reassigned. So let me ask you a question. Is Z serving the purpose of a constant in this program? I would submit that it is. Whether it used the const keyword or not, it is a constant in practice. And therefore, every bit as much in the spirit of functional programming. Now, I know many functional programmers that are absolutely enamored with the const keyword. They use it all over. I don't think the const keyword buys anything for the functional program. Because the real important key is the variable getting reassigned, not can it be reassigned. And in fact, more important even than whether it gets reassigned or can it be reassigned is it obvious to the reader that it can't be reassigned, that it doesn't get reassigned? Is that obvious? Const has some problems because it looks like it's making values that don't change when actually it's making variables that don't get reassigned. We're going to come back to that.
It's making variables that don't reassign.
But I would submit to you that in this program, Z still serves that role. And
Reassign or redeclare.
When it's called on line 11, that's still a pure function. But none of you seem to raise your hand and yell at me, wait a minute. Why is it a pure function when we're using another variable called add2, which is a variable that happens to reference a different function? You see how easily you just skipped right over the usage of that variable and zeroed in on the Z variable and said, wait a minute, that one, that's a problem. Why is it that we get to use the add2 variable? Just because it points at a function? I have news for you. The add2 variable, the reference, the identifier that points at that function from line 3, that identifier is not a constant. It is in fact possible that add2 could get reassigned somewhere to a different function definition. So it's no more a constant than is var Z, and yet we can still say that in this program, we can see that add2 does not get reassigned.
Exactly.
The behavior of line 11 is still that we observably have a pure function. Functional programmers, by the way, they do this all the time, and I don't hear them talk much about it. It's just one of those things that they assume you get. That if you're referencing a thing that doesn't ever change, it's exactly as if it had been in line, which is the whole point of constants. Functional programmers use functions inside of other functions all the time, and they don't always pass those functions in. You don't always see the Ramda utilities getting, 14 Ramda utilities getting passed in as inputs to a function, and yet you can still use them because it is assumed that Ramda and all of the methods on Ramda are, in practice, constants.
So reference.
Change their definition throughout the lifetime.
They don't change the definition during the lifetime of the program.
It emphasizes our responsibilities, the author of the code, to make it as obvious as possible that something is a constant. Don't change their definition throughout the lifetime of the program. And why I'm hammering on this point is because it emphasizes our responsibility as the author of the code to make it as obvious as possible that something is a constant, that it's going to behave as a constant. One way you could do that is with the const keyword, but I don't think that is the most effective way to do it. Matter of fact, because of the baggage that const comes with, I don't think it's actually serving a net benefit to your program. More on that later, as I promised. But whether you use the const keyword or not, if you make it obvious to the reader that it's going to behave as a constant, that's the key. Why? Why though? It's because we want the reader of our code to understand, oh, I don't need to worry that thing changed. If they were trying to understand line 8 and they didn't know that Z was a constant, well, now all of a sudden they're dealing with all the problems that you have to deal with when you juggle sign effects, right? As a matter of fact, if they really didn't know whether Z got reassigned or not, how many lines of code would they have to execute to convince themselves what line 11 would do? Well, actually, they have to mentally execute lines 1 through 10 to get to that point. Because theoretically, at least, any of those lines could have changed Z. So if they're not sure whether it's going to stay that same value, it's going to act as a constant, then essentially to read your code means they have to execute everything before a line to understand that. That's the real problem with side effects, is that it creates this outcome, which is that to understand any given line, we have to mentally execute everything before it so that we know what state the program was in before we ran it. But if the add another function call is
we need to run the entire program to know until this point.
I can execute line 11 completely in isolation of all the rest of the program. Not only do I not need to run anything before line 11 to figure out what line 11 does, I also don't need to worry that line 11 is going to affect anything else in the program. That's the real benefit of integration. It isolates that line so that I can analyze it. Here's a different usage. You've probably seen so these pure functions that we're talking about. Then I can execute line 11 completely in isolation of all the rest of the code. Not only do I not need to run anything before line 11 to figure out what line 11 does, I also don't need to worry that line 11 is going to affect anything else in the code. That's the real benefit of integration. It isolates that line so that I can analyze it.
So the value proposition of pure function is that I can analyze that line of code independently without knowing, without needing to know the state of the program at that moment. So with pure function, I can analyze that independently without needing to know the state of the program. Okay.
Here's a different usage. You've probably seen functions used as values here. I'm returning a function back. So I have this function called add another, which takes in Z as an input. Now, it's not a constant in the global scope. It's a parameter that is passed in. And you'll notice on line 7, this little strange thing that's happening is that when I call add another the first time with the value 1, that gets assigned to the Z parameter. And I get back an add2 function that is referencing Z. Right? And then I execute that function that came back, which we know here to be called add2. I execute that with the second set of parentheses. There on line 7. That second set of parentheses is executing an inner function that got returned back. And when that function runs, it is referencing a variable outside of itself. That variable was not declared with a const. It's a parameter. But what's interesting about this code that was not true of the previous slide is that this code has a smaller surface area that we need to worry about with respect to whether Z gets reassigned or not. If we want to ask ourselves, is Z in effect a constant? There are only two lines that we need to concern ourselves with, line 1.5 and line 2.5. They are the only two lines in the entire program that could possibly reassign Z. You see the difference between that and the previous slide, where there were 11 lines that could have theoretically have reassigned Z. But because of the structure of this program, I've reduced the surface area where reassignment could occur. As a result of reducing surface area, my argument is we're increasing readability. We are increasing the confidence for the reader of this code that when they see Z passed in as 1, they know it stays as 1 from then. Okay? You had a question?
Is to be considered currying?
That's a great question. We are going to get to curry. So the question, if you didn't hear it, was, is this curry? It is, in effect, a partial application.
It's partial application of a value.
Could also label as curry. But we want to dig into that topic more. So hold on to that question until we get to it. Yes, we are providing some input now, remembering that input until later. That is in the general scheme of things. Partial application. All right, so our inner function using that C variable, by the way, is using closure feedback. We're not closure section discussion. By remembering and using a C variable that doesn't change, it's in effect a constant, and therefore both the outer function call, the one with the first parenthesis set, and the inner function, the one that is executed with the second parenthesis set, line 7, both of those function calls are pure. That is to say, they have the predictability that we need and expect out of pure functions. Okay, what about this function? GetID. And we have an obj parameter, and it looks like basically all we do is access.
So
There's a different usage. You've probably seen functions use these values here. I'm returning a function back. So I have this.
but it's reducing the surface.
It's not a constant in Loboscope. It's a parameter that is passed in. And you'll notice on line 7, this little strange thing that's happening is that when I call add another the first time, with the value 1, that gets assigned to the Z parameter. And I get back an add 2 function that is referenced with Z. Right? And then I execute that function that came back, which we know here to be called add 2. I execute that with the second set of parentheses. There on line 7. That second set of parentheses is executing an inner function that got returned back. And when that function runs, it is referencing a variable outside of itself.
It's reducing the surface area because it's reducing the number of line of code.
But what's interesting about this code that was not true of the previous slide is that this code has a smaller surface area that we need to worry about with respect to whether Z gets reassigned.
Reducing the surface area. So unlike the previous code, so unlike the previous snippet, when we have to care a lot, when we have a lot of lines of codes to care about if a value is reassigned, now by returning or by using this technique of returning a function from a function, we are reducing the surface area in which a variable is reassigned, therefore increasing the readability and code provability. Crap. Which is with this. No. Is no. Really? That French toast?
If we want to ask ourselves, is z in effect a constant? There are only two lines that we need to concern ourselves with. Line 1
Exactly.
and a half and line 2 and a half. If we want to ask ourselves, is z in effect a constant? There are only two lines that we need to concern ourselves with. Line 1 and a half and line 2 and a half.
If we want to check if c is a constant, there is only two lines that we can inspect about. So line 1 and 2 and a half.
They are the only two lines in the entire program that could possibly reassign z. You see the difference between that and the previous slide where there were 11 lines that could theoretically have reassigned z. But because of the structure of this program, I've reduced the surface area where reassignment could occur.
So reassignment. So the reassignment surface is being reduced. Therefore, improving readability.
As a result of reducing surface area, my argument is we're increasing readability. We are increasing the confidence for the reader of this code that when they see z passed in as 1, they know it stays as 1 from then. You had a question?
Is B considered Korean?
Oh, okay.
Music that doesn't execute, that is to say, they have the predictability that we need in calls. Call the one with the first parenthesis set and the inner function, the one that is executed with the second parenthesis set, line 7. Both of those function calls are true.
It's interesting. It increased the confidence in our code. You fucking hit. Shit. This is mind bending stuff. This is way mind bending stuff. So add another, and add 2 are pure functions. So add another and add 2 are pure functions, since this doesn't since we can analyze the functions independently with, oh my god, since we can analyze the function independently without knowing the state of the program at that state, at that moment. And that is something powerful here. That's one of the reasons why these functions here, nested functions, not only reduce the assignment inputs, all right, the input surface reassignment area, but also increase the readability and the confidence that this variable or this input won't be reassigned. Holy moly. Therefore, making this a pure functions, and with that is increase the confidence that this function can be analyzed independently without knowing the current state of the program at that moment.
That is to say, they have the
Holy moly, bro.
Okay, what about this function? Get ID. And we have an obj parameter. And it looks like basically all we do is access the ID property on that obj. So let me ask you this question. If I were to call get ID over and over and over again with the same object, would I get the same value out of it? I see different answers. Some of you nodding your head, some of you shaking your head. So think about it this way. How sure would you be if you saw this function, if you saw this thing, which is either a function or a procedure, if you saw this in your application, how sure would you be at its predictability? That every time it's called, it's always going to get the same response? Well, one question you would ask is, does that object get mutated? Well, let's say you would answer that. Let's say in all places that you saw get ID being called, it was always the same object, and the object was never the subject of any reassignment. Then would you say, yeah, I feel pretty confident? Object, and the object get mutated. Well, let's say you would answer that. Let's say in all places that you saw get ID being called, it was always the same object, and the object was never the subject of any reassignment. Then would you say, yeah, I feel pretty confident? What if I reveal a bit more of the program and I say, what if that object doesn't have a regular property but rather has a getter? And what if that getter returns random numbers? All of a sudden, now that I've revealed more of the program, our confidence level tanks, right? Down to 0. You see what I'm saying is that it's important for you to be able to see the entire program, or better than that, it's important to be able to see all the relevant parts. The more that you can use the techniques that we're talking about in this course to reduce the surface area where these non-functional things can occur, the easier it is for somebody to read, understand, and ultimately to rely. We want the reader of our code, which is not just other people on our team, it's also our future self tomorrow and the next day when we don't remember why we wrote the code that way.
Exactly.
Whoever it is that's reading the code, we want that person to be able to tell, yeah, I know, we can trust that. It's definitely good. Because if they can, then they can move on to other stuff. If they can't trust it, they can't move on. So the thing that I'm getting at here, this is super critical for you to get. The thing that I'm getting at, the principle that I'm getting at, is that pure function calls act in isolation. In other words, given the same inputs, they always produce the same output. That's another side of the Rubik's Cube. If you're looking for another component of the definition of a pure function, it is to say that a pure function is one where every time we execute that function with the same inputs, we absolutely, positively know it will always be the same. And here we know it won't, right? Here we know by definition, if I call that same line 5 over and over and over again, we know we're going to get the answer. Otherwise, something's really wrong with our language. Right? So that's the key, is that we want to design our program so that as many of our function calls are like that as possible. As much as possible, we want our function calls to behave as pure, meaning that every time we give it the same input, we get the same output. There's more to the Rubik's Cube. We'll go back to those in 2 minutes.
Same input, same
What I'm
output.
getting at here is that function purity,
Same input and same output. Again, this is another property of this. Say input, same output. This is another feature that we must implement in our function definition and our code.
is a level of absolutely, positively know that it will always be the same. And here we know it won't, right? Here we know by definition, if I call that same line 5 over and over and over again, we know we're going to get different answers. Otherwise, something's really wrong with our randomized check. Right? So that's the key, is that we want to design our program so that as many of our function calls are like that as possible. As much as possible, we want our function calls to behave as pure, every time we give it the same input, we make it the same. There's more to the Ruby suite. What I'm getting at here is that function purity is a level of confidence. It's not a binary.
Function purity is a level of confidence.
Over the break, I was asked by someone, what if there was like a syntax that we could say, this thing is definitely true, or through errors or not. And it's missing the point of JavaScript and the point of function purity, because the point of it in JavaScript is how confident are we going to be.
Confidence.
In other words, from here on out, in our discussions, when I ask you the question, is this thing a pure function or not? The wrong answer is yes or no. Because it's not a binary question. The right answer is, I have a high degree of confidence that it will be pure. Or I don't have very much confidence.
Function purity is about level of confidence here. Function purity, level of confidence. So anytime that you have a function, it's an interesting why Redux is so powerful, this particular pattern of state management, and how that now still being relevant in today's, and how, yes, so anytime that you have a function, level of confidence, function purity and level of confidence, so anytime you have a function, so anytime that you have a function and ask yourself, is this function pure or not? The wrong answer is to say yes or no. The right answer is you have a high or low degree of confidence in your code. Confidence in that function. Because again, functions purity provide now this ability to independently analyze it. Since function purity provide a way to independently analyze that function without knowing, without having to know the state of the program at that moment.
That's really what we want to get. We want to be able to get those sunglasses on so that when we look at our code, we see that. We see the parts where we have high degree of confidence, and we see the parts where we have low degree of confidence.
We want to have those sunglasses that we see things part in our code with high confidence and others with not that much.
And we want to shift that balance as much as possible to the high degree of confidence. That is the part of function.
and shift that as much as possible to a high degree or high confidence, and shift that as much as possible to a high confidence spectrum, to a high confidence.
That is the high degree.
To a high degree of confidence. That's the heart of functional programming.
That is the heart of functional programming. Using pure functions as much as possible. And remember,
Function purity is about call, not definitions. Remember, function purity is about calls, not definitions.
your calls, it's important. Function call is pure.
What we care about is that the function calls behave pure. Okay.
Okay, so if a function is not pure for any of a variety of reasons, what are our options? One option, the obvious one, is leave it impure, and that's just about it, right? It's got to write to the database. There's no way around it. Database writes are an impure. They are a side effect. They have to happen in our apps. There's no way to get around it. We can certainly be obvious about it. We can name that function so that it is clear. Actually, we can name that procedure so that it is clear that it's
Exactly.
something like write to the database. We can even put a comment there like Darby Dragons, side effects, beware, right? We can put it in a file called sideeffects.js. We can be obvious about our side effects, and we said earlier the reason for being obvious is so that we make it easier to use. Well, we do want to reduce them as much as possible. And one of the key techniques for doing that is to take a function that may have a side effect in it and ask, is there some way for me to rearrange the way this function works and extract out the impurity, leaving just a pure function in place? That does not mean to remove that impure functionality. It does not mean to take that out of the app. You have to write the database.
Exactly. Or perform some sort of that.
It doesn't have to belong right there. If I have this set of code that's doing a very important set of computations on some kind of inputs, and then it's going to write it to the database, the functional programmer says, well, that could be two separate inputs. That could be a function that does all the computation, and it could be a procedure that does a single cycle. So what we're talking about is to extract the impurity, to bring it to the edge, to bring it to the outer shell. That is one way of making side effects more obvious. Instead of hiding it inside of the definition of this thing that looks like a function, but it's actually a procedure, we bring it to the surface, and we make it more obvious. Example, here's an add comment, which is going to construct an object and put some values into it, and then it's going to append it to the DOM. It's an impure function, right? That is,
Yes.
line 11 is an impure function call because we create a side effect with it, which is that we modify the state of DOM. But there's some interesting and useful stuff happening here that is separate from the side effects. Matter of fact, not only is there the side effect of adding to the DOM, but you might not have spotted the side effect on 3 generating a key value. It's also separate. So So is it possible for me
Because it's generating is a new unique value.
make that be an edge, make it become a
It's
shell,
a randoms.
and not the opposite? Sure. How about if we change this code to look like that? We now have a not procedure called add comment, but a function called new comment, whose only job is to make a new comment object. But you'll notice now that it receives the comment ID as an input. We take comment ID, the unique ID generation, and we pass it in as an argument. And then instead of mutating the DOM inside of new comment, we return back the DOM element. We return back the thing that is the DOM element, and elsewhere we do it. And that doesn't get rid of the side effect. It just extracts it to leave pure function wherever possible. That's what a function means by making pure functions. And then having
Function call.
wherever possible, look for an opportunity to extract out the impurity, leaving a pure function. That will not always be practical. It will not always be practical to do that, but wherever possible, this is better than leaving something as an impurity. If you can't extract the impurity, another way of getting around the problem of function impurity, the pollution that it has, the polluting effect that it has in the rest of the code, another way to do that is to contain it. What do I mean by contain? This is
Wrapping
sometimes
this into function.
It is not that we don't make impurity happen. Like impurity may happen.
No, exactly.
But
It
there's
needs
some
to
way
happen.
for us to structure things so that the impurity does not affect other parts of the application. If there's some way for us to reduce the surface area,
The surface area of impurity.
we've had a net overall benefit to our application. In other words, if the side effect can pollute the global scope, that's bad. Right? But what if the side effect that has to happen only has to affect 5 lines? That's a lot better than affecting the entire global scope. So sometimes we can't get rid of the impurity, but sometimes we can simply contain it. We can reduce the surface area. One way of doing it. Here I have a sum API. It's got a method on it called is below threshold and some value on it. What's important here is that I call that method. I'm going to modify the numbers array, but I'm calling line 11 sum API.is below threshold. I'm using that. So sum API is provided to me by like a framework or a library, and it has a function on it that I want to use. Well, one thing that I can do, if I don't want to modify the global numbers array, and I don't want to use this sum API dot is below threshold, if I don't want to use those side effects, one way of doing this is to wrap that entire function so that the side effects that occur are not in the global scope, they are inside the function. Let's do that. Let's wrap the insert sorted descending. That was the function that previously existed in the global scope. We wrapped it in another function called
Exactly.
Notice there is still line 7, a global variable called numbers. There is an array, but notice now there is also an array, line 10, inside of get sorted numbers. There's an array there that when insert sorted descending is called and line 20 tries to modify it, it is now modifying the array from line 10, not the array from line 7. And what we did on line 24 and line 25 and 26 and 27 and 28 is we passed in the one from the global scope. And then line 10, we made a copy of it. So as to not modify the global numbers array, only modify the local numbers. Did you see how I contained the impurity? There is an impurity happening. I am modifying that array. And I'm modifying it by reference, and it's a variable outside of myself. That's a side effect. But I have contained that side effect to lines 9 through 22 instead of the global scope of the entire array. That's one way of dealing with impurities. In this case, wrapping function. Now, I'll be honest with you, that doesn't often occur. A handful of times have I ever been able to take advantage of wrapping a function around another. But sometimes that is useful. So it's a good technique to be aware of. But there is still another problem. There is still an impurity. And the impurity is that we are using the sum API dot threshold and sum API dot is below threshold. Notice line 50, we are setting the variable. Line 15, we are setting threshold, which is modifying something we don't know. We're modifying threshold and calling this function. That's how we decide. And it really wouldn't work for us to wrap the sum API of the core function, because that's a third-party related thing. It's probably actually in a separate file. So wrapping it isn't going to work. Is there any way for us to contain the impurity when we can't just wrap a function? Here's another technique. It's uglier than this, it's worse than this, but it's better than that. The next technique that we'll look at, instead of wrapping a function around it, is create alongside of it an adapter function. So notice we're back now, line 9, we have an insert sorted description. That function is just out in the global scope like it was before. So is the sum API. But notice line 18, we have our get sorted nums alongside it, instead of wrapped around it. And notice what's important here is that I first make a copy of the current state that is going to be modified. I take some local variables called the ridge numbers and the ridge threshold. I get copies of those current values. And then, line 20, step 2, is I set up the environment to be what I want it to be, which is that numbers is a copy of this array. Okay? It's a copy of the passive part. And then I call the insert sorted descending. That's our thing that does all our side effects that we don't like. It's going to make changes to that global variable numbers and that sum API.threshold. Both of those are going to be changed. They're going to be modified as side effects. And then on line 22, step 4, we capture that changed state. In this case, it's only the numbers array that we care about. We capture the new changed state. We save that. And the most critical piece of all, line 5, we return all of the state that was modified back to its original value. Finally, line 24, step 6, we return that new state. This is very brute force. It is very ugly and would get very unmanageable very quickly if we had a more complex set of state, like, for example, the DOM. Capturing the current state of the DOM, modifying it, and then resetting it is hard. Possible, but quite difficult. Capturing the current state of your database, modifying it, and resetting it, really hard. Possible, but probably not worth it. But in this particular case, we had just a couple of variables that were getting changed in a way we didn't want. So
it's capturing that state.
From the beginning of the get sorted nums call in line 27 to the end of that function call.
It's capturing the entire state, bro.
Everything's all messed up. But by the end, it's all back to the way it was. So we have contained the observability of that side effect in the function. Even though get sorted nums is not actually a pure function from this technical definition, we have achieved the more important outcome, I argue, which is that line 27 runs as a pure function call. It satisfies all the conditions that we want out of a pure function call, which is that it takes direct inputs, it gives us a direct output, and it doesn't change anything else about the state of the program afterwards. And it didn't rely upon anything about the state of the program before. Those are all the things on our checkmark list that we want, and line 27 fulfills it, so does 28, 29, 30. So this is another way of healing the side effects. Contain their effects, in this case, containing the function. Sometimes they're going to happen. We want to reduce the surface area of the side effects happen at all costs. And if none of these things work, if you can't write it pure from the beginning, if you can't refactor it to be pure, because now you know that's important, if you can't extract the impurity so that it leaves a pure function, if you can't make a wrapper function around it, and you can't make an adapter function, if you tried all 5 of those things and none of that worked, you're stuck with a side effect. At least make it obvious. Contain it somewhere, make it obvious, so that if there are bugs, future reader of the maintainer of your focus. How do you feel about side effects? Give me a thumbs up, thumbs down. How are you doing so far with this idea of side effects using pure function? Yes?
I've heard before that also mutating state of parameters is also considered to be
Okay, so the question is, if I have a parameter that's passed in, and I mutate the state, unfortunately we need to be more specific around that word. So let's look, for example, at the insert sorted descending function. I'm just
Line
passed in numbers rather than referring to global. But I still call numbers.splice on line 15. Or if we consider the previous slide where I was doing it on the array numbers. In both of those cases, I would be modifying the value by reference. So I'm not actually changing the parameter. I didn't reassign parameters of different value. I used a reference to mutate the value of a distance. Using a reference to mutate a value of distance is absolutely a side. That's the whole reason we wanted to avoid the number of splicing. But that is definitely a side. But taking a parameter that, say, was passed in as a value 4 or even an array, and reassigning it to point to a different value, that doesn't have any effect on the output.
No, that doesn't have any effect with the also.
Mutate a parameter, you have to ask, are you mutating the value of the parameter references? Or are you mutating
What assignments this is?
the former of those is a bad side effect, the latter of those is totally fine.
Exactly. So you're mutating is the value of a reference that you're receiving, of course.
Topic of maintaining function keyword.
Okay, that'll be all for this video. Take care. Bye bye.